Okay, good afternoon everyone. Thank you for the introduction. Thanks as well for the invitation to come and speak today. It's nice to get the opportunity to come and talk about our work to new faces, so thanks for that. I did have a look before putting this talk together at some of the talks that you'd had in the other seminars previously this year, and I think the topic probably is a little bit different, but I hope different doesn't necessarily mean bad. Hopefully you'll find what I'm going to say interesting. So a quick overview of what I'll talk about today. I'll start by talking a little bit about thermoelectrics and kind of why it's an interesting topic, why I think it is, where it fits in, and some of the kind of applications and those types of sort of more sort of overview type things. I'll also talk a bit about thermoelectric performance and why, what makes a good thermoelectric material or device. That'll bring me on hopefully to silicon, why we'd like to look at silicon for thermoelectrics, and then I'll talk a bit about defects, because it's creating defects in silicon that we use as a strategy to try and improve its thermoelectric performance. So moving on from there, I'll talk about a couple of approaches and sort of results, and then what we see as some sort of things moving forward, so the next few things that we might do, and finally some conclusions. So starting off with a bit about thermoelectrics, it's an interesting technology, or I think it is, because it allows us to interchange between heat and electricity. And you can see on the schematic here, we have the device in the middle, we have heat absorbed on one side and heat rejected on the bottom. And as the heat passes through the device, some of it can be converted into electricity, and we can take that out using an external circuit. So the devices are quite straightforward, as you hopefully can see. We tend to have a couple of ceramics, top and bottom, some thermoelectric pellets, P&N type semiconductors as the active part in the middle, and then those are hooked up in with metal interconnects to keep everything hooked up in electrical series. And you can see here a close up there. And this down in the bottom left hand corner is kind of a real device. So the photograph looks quite like the schematic. So quite simple devices. This is on the scale of about 3 or 4 centimetres by 3 or 4 centimetres by about half a centimetre thick. So quite small devices, but they can be scaled to various sizes. Why are they interesting, and why are they kind of getting renewed interest at the moment? Mainly because we're looking at the ways we use energy more and more, trying to be more efficient how we use energy, less wasteful, particularly with heat energy. There's about 15 terawatts of heat generated on average all the time that could go into waste. So thermoelectrics is one technology that we can use to try and recover some of that energy and reuse it for useful means. So it's not always the best technology to use for this, but there are some situations where it probably is the best and where it is useful. One example being on car exhaust systems. So BMW are one manufacturer interested in this. There's also Volvo, Volkswagen, General Motors, all looking at ways to generate sort of tens to hundreds to thousands of watts using heat from the exhaust system to generate electricity on board. And this allows us to potentially replace things like the car alternator, improving fuel efficiencies, maybe up to about 10%. So this doesn't sound huge, but if you think on a large scale of all the cars being manufactured every year, all the CO2 emissions that relate to that, it's quite a potential large impact. So that's kind of at one end of the scale. I should say as well, this isn't really suggested as a technology for large-scale energy generation to compete with things like fossil fuel generation, wind, wave energy, these types of things. But tens, hundreds of watts is possible for some applications. At the other end of the scale, certainly energy harvesting and sort of self-powered devices, particularly things that can work on microwatts, milliwatts, so things that can then harvest the heat from the body, are particularly interesting for using thermoelectrics. The devices then look pretty much the same, but they're just a lot smaller. So this is just you see with respect to this coin, pretty small device, but essentially the same structure. There are also additional applications. So space is one, and that's probably the big traditional one, more at the higher end of those power magnitudes. And you can see the image here from NASA. This is of a radioisotope thermoelectric generator for the Voyager mission. So this uses radioactive decay, the heat from that, to power the device and produce consistent power for a long time. And over many decades, these devices can continue to produce electricity, which is pretty useful for these applications. So we also have things like satellites, wireless power, in situ process monitoring, sort of powering of sensors, all its potential applications. So particularly useful where we have sort of remote type of applications. Over on the right-hand side, you can just see here, this is a graph of generation efficiency, of conversion efficiency, as a function of, this is the hot side temperature of the device, and with a cold side temperature kept the same. And you can see the kinds of levels of efficiency that we get. So we have in this efficiency equation a Carnot dependence, and we also have another term here that's pretty much dependent on the material, these thermoelements that sit in the middle of the device. And I'll talk a bit more about those in a little while. But effectively, these have the effect, the better the material is, the better the conversion is, the better the efficiency, as you probably won't be surprised to hear. So I'll come back to talk about ZT a little more in just a minute. The flip side of the devices is that, as well as using them for energy conversion, you can also use them as heat pumps for heating or cooling. So instead of using the hot side, cold side gradient to generate current, you can put a current through the device and move heat from one side to the other. Again, this is better for the small scale, so I'm not suggesting this type of heat pump could compete with air source or ground source heat pumps, but for small scale applications, the solid state type of application can be quite useful. So there are applications being looked at such as hybrid electric vehicle battery temperature maintenance, heating within seats and things like that, cooling of electronics, so chips getting very hot and trying to cool them down. We can look at sort of precision temperature control applications, and also things like camping stoves. There was somebody on Dragon's Den you may have seen who had a device based on this, where he was using his camping stove to cook, but also to generate electricity to charge his phone while he was out camping. And just on the left here, so just some sort of theoretical and some experimental data, just to show you can get some reasonably respectable coefficient of performances from these types of devices as well for the right applications. So that's kind of an overview. I'll talk now a little bit about the materials and kind of why silicon. You kind of heard from my background that I have a background in silicon, so that's kind of why I'd like to focus on that in one respect. But there are lots of advantages silicon has over some of the traditional thermoelectric materials. So you can see them listed here. So the first two, bismuth telluride and antimony telluride, tend to be used when we have temperatures, waste heat in the sort of 100 up to, or say room temperature up to a couple of 100 degrees. If we go slightly higher, 400-500 degrees, lead telluride tends to become the material of choice. So we have tellurium in all of these. It's the 8th rarest element on the planet. It's fairly scarce. The materials are quite expensive. We have lead in one of them. They're not really manufactured at scale and not particularly technically mature. And this is counter to what we have for silicon. Of course, we have it's abundant, it's low cost, even very high quality, very pure material can be got relatively cheaply. We're used to handling it every day in devices. It's mass manufactured, and we have big technical know-how as well on this material. But the big issue is that it's a pretty rubbish thermoelectric material, so that's a pretty compelling reason not to use it for thermoelectrics. And we know that because we can look back at this ZT that I've mentioned already. Just to say a little more, the ZT, the Z is the figure of merit. It's usually described in this way, multiplied by T, because that makes it unitless, so we can just give a number in order to compare materials. But it's basically the higher the better, and it's determined by these material properties here. So we have the electrical conductivity of the material, its Seebeck coefficient squared, and divided by its thermal conductivity. So this is where the real challenge is with thermoelectrics. So you can see we need a good electrical conductor, a poor thermal conductor, which tends to be difficult because usually the two go hand in hand, and when one is high, the other is high. So bismuth telluride is pretty good. It's a good combination of the three. Silicon competes well with it on the first two, or can do, but the thermal conductivity tends to be about 100 times higher. So you can see the ZT is 100 times smaller, way, way worse performing in general. So the challenge we were looking at, and the challenge others are looking at too, is how to try and reduce thermal conductivity without affecting any of the other properties that are good. And the main approaches to do this are looking at nanostructuring of the materials. So there's been a big sort of activity since about 2008 where there were a couple of papers in Nature back to back, and they looked at silicon nanowires for thermoelectrics. So in this case, where you have nanowires instead of bulk material, if you make the nanowire such that its diameter is below the mean free path length for phonons in silicon, which is about 300 or so nanometers, you can significantly reduce thermal conductivity without affecting any other properties. So it's quite a nice way to do things. This is kind of a one-dimensional structure. You can do the same with two-dimensional structures like nanofilms. So if you make the thickness very thin, you can also reduce the through-plane thermal conductivity. And people have also looked at sort of porous structures in thin films, some very regular, very dense pore structures like you can see here on the right, also work quite well at stopping phonons travelling through this film. The main issue, I guess, with these is they're pretty different to those pellet structures I showed you right at the beginning. Those sort of chunks of bulk material, very different to these nanostructures. So as interesting as these are, the challenges really have been engineering ones, how to make these into real devices. So we wanted to look at methods that didn't involve or didn't rely on nano dimensions, and ways to try and apply this to sort of scales that are a bit more applicable to devices. So you saw those thin film devices and also the pellets I've shown already. There were numerous studies in the last few years from molecular dynamics looking at the effect that vacancy defects in the silicon crystal could have potentially on the thermal conductivity and reducing it down. And this can be quite a huge reduction, as you see here. There are various magnitudes from these different studies, but this is a kind of I suppose a typical prediction. So 95% reductions, 1.5% vacancies. The issue really being how to get 1.5% vacancies and how to kind of keep them in the structure is fairly difficult. So we came up with the approach of what we call vacancy engineering to engineer vacancies, and I'm just going to show you a kind of little cartoon of sort of how that works. So basically these 12 blobs here are supposed to represent silicon atoms in a nice silicon crystal, and the one out on its own here is supposed to be a silicon ion. It's part of an ion beam that's going to impinge on the surface here. And this represents silicon ion implantation, which we use as the experimental means to do this vacancy engineering. So basically what we have is the ion comes in, interacts with the atoms in the nice crystal positions, and it creates a bit of damage. And obviously this happens over a much wider scale, but this is just a quick cartoon of what we think happens. So we get our silicon atom ends up somewhere in the substrate. We also get a lot of vacancies where the atoms were in the host lattice, and we get interstitial silicon that's moved out of its original site. And we get something like this. And when we do this over a large substrate, so we get something a bit like this. If this line is the surface and this is into the depth of the crystal. So we get our silicon ions with this type of distribution. We get a lot of interstitials created, and just slightly shallower we get the vacancies where these interstitials have originated from. Now what we can do, if we anneal this, so very short, low thermal budget thermal treatment, we can allow a local recombination of these vacancies and interstitials, and basically what we get is sort of a net of adding up with the silicons and the vacancies locally with respect to depth. So if we add these up, we should get something that looks a little bit like this. What we can do as well to sort of test or proof of principle of the experimental effect of vacancies is if we use a substrate that contains a buried interface layer, so we use a buried oxide in the silicon, we can isolate this top layer of silicon, and then we can see the effect that these vacancies have. So that's the principle. So we've used simulations to kind of inform our experiments and decide on experimental conditions. So this is basically, again, this is depth. Oh, okay, carry on. This is depth versus concentration of defects here. So we have silicon at the top, the buried oxide, and then silicon below. I'll point out at this stage that for this proof of concept we do use a very thin layer. So I said we wanted to get away from nano, and we will come to that in a bit, but just for this concept, just for this part, we are using 100 nanometer film. So we put in silicon, this is the green here, and we get vacancies, which is the blue dash, interstitials the red dash, and then we look at the net effect of this. So we get vacancies in this top layer, which is what we wanted. So I'll just quickly touch on the electrical properties. These are the ones we didn't really want to change. So we chose a nice highly conducting top layer, so phosphorus doped with a good electrical conductivity. And the basic thing here is after implantation we reduce this down because we create a lot of damage. But after our thermal treatment, this almost recovers. So we've got our doping density here and our mobility of electrons here. They're not quite recovered fully to the control samples, but they recover somewhat and pretty close to what we had originally. And the reason we don't quite get recovery is in this very near surface region where we have the most vacancies, we still see some degradation of electrical properties. So in both mobility and carrier numbers. When we include our Seebeck coefficient, so looking at the thermoelectric power factor now, which is basically, so it's the sum of the Seebeck, it's the product of the Seebeck coefficient squared and the conductivity, so it's this top part of the ZT. Bringing Seebeck in also, we see the same sort of thing, so we're almost recover our electrical properties quite well after thermal annealing. But the thing we're really interested in is the thermal conductivity. So in our control sample we have about 65.3 watts per meter per Kelvin as our initial starting condition. Immediately after implantation, like the other numbers, our thermal conductivity drops way down. But the interesting thing is when we do our anneal, so this is anneal at 600 degrees, I think I forgot to say. When we do our anneal, the recovery in terms of thermal properties takes a bit longer. So we have this window where our thermal conductivity stays low, but our electrical properties are nice and high. So this gives us this, when we combine this with our power factor, so our thermoelectric figure of merit in this central region peaks at almost about 0.2 at 360 Kelvin. Which is about 20 times better than the control sample down here. I should say it's still a little way off what we saw for what we get for bismuth telluride, but you know, as a first attempt, we don't think it's too bad. We still have some optimization that we can do here. It also, I would say as well, compared to other nanostructuring approaches, it's quite competitive to those. So some of the ones I showed you before, like the nanowires and the porosity approaches, but this process is a lot simpler to do. It's a staple method using silicon CMOS fabrication. You don't get sort of very fragile structures. You basically get a material that looks the same before you started. So some issues that we're looking at and have looked at a little bit already with this. So we do get this evolution, as you saw, of thermal conductivity as we up the thermal budget. So this is to do with the defect evolution. So we know the vacancies evolve when they're exposed to thermal processes. So we get clustering, and we get eventually dissolution of the defects as well. So as they get bigger, the theory predicts that they'll be less effective at doing what they're doing. Also, as they disappear, obviously there's less of them, so we return more towards what we had in the first place. So it's maybe not surprising that we get this effect. This could be a problem, of course, because thermoelectric devices, as I've hopefully showed you, the whole point of them, the whole job description is that they have to work at relatively high temperatures. So if they're not very stable with temperature, that's a problem. But I'll just point out again, we did this annealing at 600 degrees. We're proposing that this would be a better type of approach to use at more low temperatures. So we're thinking more competitive with bismuth telluride. So temperatures around about 150 degrees for energy harvesting. And what we've done, when we take these good samples, or these optimal samples, and these as implanted ones, and we do some post-annealing on them, so we put them in a furnace for a couple of weeks at relatively low temperatures. We don't see any difference there. So it's really, if you go to higher temperatures, then you do see a lot of evolution of the defects. If you stay at low ones, things seem quite stable, at least for 2 weeks. So that's promising so far. The other issue I would say as well is we've so far looked at our properties kind of in the in-plane direction, so measuring sort of through the length of the film. Usually the devices are made in the through-plane direction. We've done some measurements as well, looking at the differences in the thermal conductivity in the two directions, and they're not much different. If anything, we do see slightly better reductions, or slightly better values in this outer plane direction as well. So we don't think that will be an issue particularly. So I said I'd come back to scalability. Really, the processes we use are quite easily scalable. So you can up your implant energy for your ion implantation to modify the extent to which the vacancies impinge into the substrate. And you can see this hopefully here. So these are our ions at various different energies. And you can see then the net vacancy profile from the simulation that we see here. So we're still not anywhere near bulk materials, that's for sure, but with these simulations we're out towards kind of a 2.5 micron thick films, which for the thin film devices is within the range that they're being made at. So we're currently doing experiments with these types of energies and slightly higher ones too, as well to see how things work when we go to more device relevant dimensions. So one of the ways we're doing this as well is not to look at silicon with this interlayer, but is to just look at very thin silicon and basically implant all the way through the whole piece of silicon. So we've been making these very thin silicon films using kind of optimized etch conditions. And you can see when we go down to very thin, sort of tens of microns and sub 10 micron thicknesses, we can actually get flexible silicon as well, which is quite nice for potential applications in the future. So we're currently now characterizing materials. We'll then make devices is the end game, and I suppose that's where the engineering part will come in, and the difficult part will come in. But we're quite hopeful that we might find something interesting when we make devices as well. So just some conclusions on this section. So we think this is a novel concept as a way to try and improve thermoelectric performance in silicon. We can significantly reduce the thermal conductivity, maybe not as much as we'd like, but we're made some good progress. We don't really degrade the other important properties very much, and we've gone up 20 times in our ZT so far. As I've already said, some of the scalability type issues look okay so far in terms of what we've done, the due diligence so far, and we're now looking at these thin film structures and devices of that kind of nature. So I just want to touch on as well another approach that we're using to try and modify some of the properties. And again, it uses ion implantation. Again, it uses the defects created. So again, as well, another kind of cartoon type illustration of what we do. So we're again looking at kind of concentration versus depth. And if we start with crystalline silicon again, again ion implantation, again silicon. The difference here is we use much higher doses of silicon for our implant. So effectively we go so high that we completely disorder this surface region, and it goes really from being crystalline silicon to amorphous silicon. Slightly beyond this, at slightly deeper depths, we just get these excess interstitials for the same reasons as we get in the vacancy engineering experiments. When we anneal this time, and we use higher temperatures around about 900 or 1,000 degrees, we get regrowth from this interface here between amorphous and crystal. So this acts as a crystal seed, and we get amorphous, or we get solid phase epitaxial regrowth towards the surface. So turns back into crystal silicon, and because of this epitaxial process, we don't get any defects really left in the near surface. We just get, where we had this interface, we get a lot of dislocations, end of range damage from the implant. So this is much easier to see than the vacancy defects, which are you can't really see with microscopy, but you can see these with TEM. So this is just 4 examples of snapshots of parts through the substrate. So you can see the dislocations, and they vary as a function of the thermal budget applied and as the ion conditions that we use. But you can get quite a lot of defects, quite sort of a lot of dislocation loops and just dislocations as well in the material. So we've had a look at this for bulk materials, or we're still looking at that for bulk materials really, but I'll talk today on some of the work we've done on nanowires, because that's a bit more further forward. So we use these substrates with the defects in, and with silicon control wafers as well, to try and make silicon nanowires and look at the properties of the wires with and without defects. So we use a metal assisted chemical etch process to do this. So basically we take our piece of silicon and we spin on little polystyrene nanowires in solution. And doing this with spin coating, you can get nice self-assembly. So that's just a very small snapshot, but you can get quite nice self-assembly on the surface. We then use a reactive ion etch to etch these down a little bit. And we get, basically these are polystyrene sort of masks on a silicon substrate. We can then deposit gold or any noble metal, and if we put this in a HF, hydrogen peroxide water mix, then we get this metal assisted chemical etch down through the silicon where the gold is, and masked where the balls are. So we get something like this, or we can get something like this. This is just a bit of a blurry TEM, but an image of a couple of the wires, and you can see the defect region here. And we've done this, we've used a range of wires, and we've made them 10 micrometers in length, and done a range of different diameters. So between about 100 and about 1,000 nanometers. And we looked at the thermal properties of these, because we were kind of interested if these defects would act as a kind of bottleneck within the wires for the phonons to reduce the thermal conductivity down. We thought that might be possible, but actually didn't really kind of pan out that way. So you can see here, this is thermal diffusivity, and this is the different nanowire diameters. The stars are the ones without defects, and the spheres are the ones with defects. And there's a bit of variation, but there's not particularly any trend in the ones with defects or the ones without defects having any different thermal properties. And this is consistent at various different temperatures. So we didn't really see what we hoped we might see. When we go to very thin nano wires, then we do see a reduction in thermal properties, but this just agrees with what's been shown before by the Nature paper that was back in 2008. So nothing kind of particularly interesting at that stage. I'll skip over that one. We looked as well at the electrical properties. And at this stage as well, we weren't particularly thrilled with what we saw, because we basically saw that in the ones without defects, the properties were fine. But where we had a lot of these dislocations, we particularly saw the mobility of the carriers in the material reduced. This is obviously not a good thing. But we also went and measured the Seebeck coefficient of these samples. So we looked at these, measuring them as arrays. So we used a method basically from a group down in Imperial, where you measure the whole arrays with kind of a gold foil contact above and below, measure the Seebeck coefficients, and measure also for the substrate, and then try and take out what the effect is of these nanowires. So the results we saw here for, this is 3 different temperatures, and you can see the Seebeck coefficient here. This is ones without defects. Are more or less in line with what we see just in normal silicon and in bulk materials, which is these ones at the end. But what we saw that was interesting was these huge improvements in Seebeck coefficient when we have defects in the nanowires. And this was quite consistent over different temperatures, and we saw this increasing, well, at least initially increasing as we went from kind of slightly bigger to slightly smaller nanowires. And then we saw this point, which is we're still not sure about, but we certainly see some improvements here, significant improvements. So it's about up to 90% is possible. So we weren't really expecting this, we didn't predict this, but we had to look for an explanation. The one that we have at the moment is mainly related to the strain that these defects introduce into the wires. So dislocation loops in particular are known to introduce large strains in their close proximity, and this has been shown. This is a basis of what people have looked at for trying to get light out of silicon, and one means of doing that, introducing dislocation loops. So the model there in this paper from 2001 is that you get this type of band structure around the defect, where you get a kind of what's the word I'm looking for? Potential barrier. And this has also been predicted in silicon. This type of structure, or this type of potential barrier structure, has been predicted to potentially act as an energy filtering means for low energy carriers, to try and filter them out in close proximity to the defects. This would also explain a little bit why, when we go down in nanowire diameter, we maybe see a greater effect, because the carriers are effectively forced closer to defects. It doesn't explain this point here, but still, there's work to be done, and work in progress, I should say. So just to kind of conclude on that, we think as well silicon nanowires are an interesting approach to thermoelectrics. There's certainly been a lot of work in this, particularly in the US. We've tried to combine defect engineering with this approach to try and do things a little better. And we think maybe the combination of the approaches will ultimately lead to good ZTs. So we don't really see any thermal properties differences by introducing these dislocations. We actually see bad effects on the electrical conductivity, but the net effect is very positive, because we see this increase in Seebeck coefficient, and particularly as it's a square term in the ZT equation, then the net effect can be quite high. So in the samples we've looked at, we see a ZT improvement of about 2. The headline number is actually quite small, because we've used very lowly doped material so far. So the actual ZTs are small, but the increase with the defects is a factor of 2. So we think, well, we have a sort of tentative explanation of what's going on, and we're working with somebody at Warwick University to do some simulations and some theoretical work to see if this kind of makes more sense when you're looking in more detail. And so far it seems like maybe it does, but we have to convince peer review of that before we say anything too final on that. So just some final conclusions. I think I'm just about on time. So I think there's many good reasons why we might try to look at silicon as a material for thermoelectrics. There's also some pretty good reasons why not, and there's certainly some difficulties. We're trying to look at strategies that involve the introduction of defects to overcome some of these. And there does seem to be different strategies and different ways of improving the properties, so for both thermal and for Seebeck coefficient as well. Our best kind of improvement so far is about a factor of 20, so getting ZT to about 0.2. We still have some way to go, I'd say, to get truly competitive with bismuth telluride, but that's what we're working on now, alongside scaling up these approaches for thin films. And we do also have a few ideas how we might try and do this for bulk materials as well. So that's also an aim as well, looking further ahead. So just to acknowledge some other people who contribute to this work. So my PhD students Neil and Edwin, and also colleagues who work in chemistry and work in thermoelectric materials and chemistry at Heriot-Watt. So Jan Willem Bos and Srinivas Papuri. And also on the nanowire work, some colleagues in Ireland and Germany now, Dara Byrne and Aidan Cowley. And also to thank the School of Engineering who supported this is at Heriot-Watt, I should say, who supported the Vacancy engineering work. And we have some funding as well over in Ireland from my previous position for some of the work on the nanowires. And finally, to thank you as well for your attention, and I'll happily try to answer any questions that you have as well. Thank you.
This production is brought to you by the University of Edinburgh.